Alright, time for another draftphysics.com, debatephysics.com also, but yeah, sorry. Can't get anybody to debate, so just depressing, but it's the way it is. Debate in any kind of form, frankly. I mean, exchanging videos, there's so many topics, it's supposed to be science, and it really isn't. There's no real argument, there's no real investigation. There's no real honesty, frankly, in terms of what they have good evidence of. It's just all really, really bad. So we've been over the MV squared thing. It doesn't work, can't collect it. All the experiments show it to be useless energy because you can never convert it into momentum without breaking the requirement to conserve momentum. So it can be understood to be just a really bad theory. Really bad. The whole Eddington relativity thing, come on. The guy admits in his own journal 1/10 of the data quality states the actual statement, I wouldn't stake my life on these results. That deserves a New York Times headline saying Einstein proven right. No, that's not good science. Okay, never repeated, especially not repeated from space where you don't need an eclipse and it takes 5 minutes. Really 400 times better seeing. So Eddington got 10% of the data quality. So that's 10% less than what he was 10 times less than what he was hoping for. And from space, it's 400 times easier. But no, I'm doing bad science by bringing that up. That's really bad science to talk about how you could do the experiment so much better, so much easier, and we're supposed to believe it's never even been attempted. And, it's an optical experiment, so it really does prove the point where other experiments scatter can always be an explanation because they're not seeing an image. All right, anyway. It's just, this is so bad. All right, so I'm going to talk a little bit about the Bohr model, just how bad Bohr was for physics. In terms of understanding electrons and protons and nucleuses and, the whole makeup of the thing and how it's all so easy to understand, with a different model, with a model even based on just Maxwell's information about charge. Now, Maxwell, I don't know why he messed with this idea that there's no magnetic monopoles when clearly the electron and the proton are the only thing you have to work with anyway, so clearly they're both electrical monopoles and, of course, magnetic monopoles. Magnetism is just an expression of electricity, which we've already found out. So why are we pretending that the monopoles wouldn't be the same things? And if you think in those terms, you can also think about how magnets would behave if you could create a little north side magnet over here and a south side magnet over here. And what they would do when they stuck together, which is create a dipole. And then you could think about that in terms of how you could have different arrangements of that dipole. All right, so we know some things about atoms, like, this idea that, there's something in the nucleus. Okay, I should probably draw that red since it's net positive. All right, so it's got twice as many, generally speaking, you could argue, positive elements than it has negative elements. And so let's just quit pretending we don't understand that neutrons are electron and a proton. Okay, so a neutron is just an electron, and a proton, you could argue, very close to each other. So it's a hydrogen atom, essentially, except it's compact. They've gotten very close to each other, and that's what's inside the nucleus. And so there are technically electrons inside the nucleus. It's not void of electrons. It's just that it has 1/2 as many. Okay. And then the rest of the balance, what balances the charges, are the fact that the rest of the electrons are lining up with that nucleus. Now, how much distance there is, okay, we're basing all that on one experiment where they shot pieces of radiation at atoms and then figured out how much bounces back. Now, you could argue that the only one that bounces straight back would have to hit right on the center of the mass of the nucleus, and if it hits anywhere else, that it's not going to bounce back directly, okay? And there's lots of opportunity for it to just be bent as it goes through and come out the other side at some angle. And so, I haven't gone through all those the Rutherford experiments in detail, but I tend to think that they probably have exaggerated the smallness of the nucleus and the distance of the electrons, but whatever. For the sake of this argument, that won't be a necessary conversation. All right, so we all hear about what they say happens inside of suns and fusion and all this kind of stuff, and how they're making energy by combining 2 hydrogens or 3 hydrogens. It's, and they say the word hydrogen, and there's all kinds of hydrogen. There's hydrogen 1 and hydrogen 2 and hydrogen 3, which means that it's really not the same thing, right? You're sort of arguing that all atoms are made up of this basic elemental relationship of an electron and a proton, okay, being associated with each other because they're attracted to each other, so it makes sense that they could get close together. And the key element, you're saying, so they even the invention of the the strong force and all that. Well, let me first just say, okay, the Bohr model of electrons spinning around the nucleus, totally unnecessary. You got to say there's so many ways to say, oh, that can't be possible, because from just all the stuff we get from space and satellites and going to the moon, that orbits are very precise. You have to have exactly the right speed, and you have to have exactly the right trajectory, or you go flying into space, okay? Orbits are a very precise thing. You have to have a very precise momentum, both angular and regular, or you're not going to be in an orbit very long. So that's a fact, and that's part of the inverse square law, in the sense that your gravity is changing as you move further away or get closer. The force is going to exaggerate the defect in your orbit and make it degrade even faster. So yeah, orbits doesn't sound like a good idea. And we know they're magnets. So we know what charge is. It's this attraction repulsion thing. So I don't know why it was so repugnant that they didn't even consider, frankly, a magnetic kind of model, where you could argue, let's just say the nucleus is net south, okay? You could really understand that you could have north magnets in a relationship to that south magnet, where their tension, okay, would make it impossible for them to, move and go anywhere. Like if this one tried to get closer to the south, it would have to push on these 2 repulsive other electrons, and that tension would keep everything at a distance and in a relationship. And it makes perfect sense if you think of the terms of a something that's, I don't know if isotropic is the right word, something more like an ion. All right, so let's say you had an atom, and you're going to combine your atom with some other atom, and the idea of you're sharing an electron, come on, doesn't it make about 1,000,000 times more sense that if something was going to, let's say this one has 3 electrons in these positions, that it would literally share the electron, that the pressure would be shared, that the electron would find a place that was empty on this atom, the key fitting the keyhole, and that there would be probably some engineering that would have to be done to make that happen. Let's say when this atom isn't sharing an electron and it only has 3 electrons, these 3 electrons would be in slightly different positions because they would try to be equidistant from each other. And when you push in this new atom to combine, you have to push it in with enough energy to push those electrons into new pressure. That is, make them a little bit closer to each other. So now they have more pressure between each other because you've added another electron. And the same rules apply, that the electrons really can't, it can't jump to one or the other without getting in trouble with the other electrons. Now, part of this explanation, you sort of have to accept that the nucleus isn't homogeneous. All right, the nucleus isn't just a net positive and it's just radiating positive. What the nucleus is net positive in the sense that overall it has more places, okay, where it's positive than negative, but it's not all positive and all negative no matter where you look at it from. So the idea would be is that you're arranging electrons and protons inside the nucleus, and you have twice as many protons as you have electrons, but there's places where you could look at the nucleus and see the negative, and there's places where you could look and see the positive. And that's what's really happening. That's why this electron doesn't just fly into the nucleus, is because the fact is this over here is a little bit, the electrons are here and here, and the proton heavy part is here. So it sees the proton, but it also sees the electrons. Can't get closer to the electrons, so it can't get closer to the damn proton. So it's always a balance of power. And we know this geometry is very, very narrow. There's only, less than, you could argue that there's only, 90 stable elements possible. So 90 stable relationships you can create between electrons and protons, stable nucleuses. And if you try to make them any bigger or change the geometry in some way, you make them isotropic, and often the isotopes will fall apart. They will decay because they're not durable. They're they're not. They don't have a symmetry or a capacity to hold up over bombardment in the universe. All right. So I mean, it's just accepted by everyone. This is the axiom. This is the truth. The Bohr model isn't proven with some sort of picture of atoms with a bunch of electrons spinning around and doing all that stuff. Now what we can surmise out of it is that there's energy in their motion, which is, I would argue, just jittering. So Einstein demonstrated that's the the byproduct of that is Brownian motion. So yes, everything's being pushed around. So at any one moment it's getting hit with a little more energy from one side, and then the next minute it gets a little more from this side, and the next minute it gets a little more this way and this way. It's not some perfectly symmetrical, over time it's perfectly balanced, but you could argue over any one moment of time, something can get hit more from one side than the other side, move a little bit, so it's always kind of being knocked out of its positions. So you could understand that's probably what hydrogen is the fact that you have an electron and a proton, and what's happening constantly is shear. So in spite of the fact that they're attracted to each other, and again, I'm not even giving you my mechanical explanation for that attraction. You already know that exists. So if you've accepted the existence of that attraction. And so part of this, I just wonder why it never even occurred to you to think about the implications of that attraction. But anyway, the idea is that, okay, there's energy pushing them together, so they do go together, but there's also force coming from this direction, force from this direction, force this way and that way. So they're constantly being pushed out of alignment with each other. So you could understand that if the thing driving them together is an actual force, and that there's a force between them that is providing the opportunity for them to move into each other, that mechanism could be disturbed by the fact that they keep moving out of alignment with each other. So they can't see each other because they keep moving out of alignment with each other. So that keeps hydrogen from becoming a neutron. And it's just the fact that when it's free, when it's not in a nucleus, it doesn't have anything to it has no mass to bind to. It has no heavy object to keep it stable. And so it's got more tendency to wobble. It's almost like us standing on Earth. Gravity is a force. It pushes us in one direction, and it's strong enough that it stabilizes us being moved any other direction. If we were in free space, it's likely we're going to drift, like, but on the Earth, less drift. That could be made as an argument. Anyway, so even if you do the Bohr thing and even all this other stuff, then you get to this idea of a strong force that drives protons into each other. That there's some kind of force, an actual new force, a mechanism that only does this one thing of pushing protons into each other inside of nucleuses and doesn't do anything else in the universe. And yet it's the breaking of that strong force that I think most physicists think or understand to be what happens in a nuclear reaction, that is a nuclear bomb, where you're getting all the energy from, is that somehow you're breaking that strong force. But the simple, obvious, to me, thing you could understand is what's happening inside of a sun is obviously it's all this stuff moving towards each other. So there's a great deal of pressure being created because you're pushing everything into one location. And obviously stuff is getting pushed this way, and it can't go both ways. So that's a lot of pressure stuff is under. And then you can understand under all that pressure that it wouldn't be difficult at all to imagine that you would have a combination of electron, proton, and electron. Or, in this case, the more relevant to you people, okay, and the idea of protons somehow being the more important agent here. Now, they could be the more important agent because they're heavier. So if they're actually correct in assessing the weight of the proton, but I don't think they really are. So that's another doubtable truth, especially when you consider they weighed the electron using 1/2 mv squared. So they used a really bad formula to ascertain the weight of an electron. So it seems clear that's probably not a right answer. Now, another giveaway is that our atomic weight is 1% of our real weight. So I mean, it's not sort of just saying to you, well, that doesn't really make sense, right? I mean, if you add up all my electrons and protons, I should be weighing my real weight. I mean, they're all I'm really made out of is those pieces of matter. So why don't I weigh what my little elemental bits weigh? And the answer is kind of, well, if I weighed this 1,000 times lighter than it actually is, then yeah, that's probably where the wrong answer came from. All right, anyway, so this, I think I saw something somewhere where they call this a deuteron. Okay, so okay, it's a good enough word, right? Deuteron, whatever. But obviously you could understand that you don't need a strong force to get a proton close to a proton. You just need an electron in between, right? So if you recognize that charge is a visual thing, in the sense that Maxwell basically proves that, in the sense that he just draws two radiators, okay, two objects radiating, and the idea is that they're combined mixture of their radiation. Like I said, he has one going as an in force and one going as an out force. And obviously what I'm arguing is it's, the fact is there's another force. There's two kinds of force. And it's just a simple argument that the red force doesn't affect the greens and the green force doesn't affect the reds, and that's why you can push them together. But anyway, you can see, I'm just saying that it seems kind of an obvious circumstance where you'd say, well, yeah, why couldn't you create something like this and end up with two protons really close to each other? And so in my model, what's really happening is it's all of the red force. Oops, wrong color. Okay, all of the red force is being converted into green force here. Okay, so it goes into the green red, comes out of the green green, okay, goes into the red green, which is meaningless to it, comes out red, okay, which is meaningless to the green, and then comes out green. So the force is just converted, and it doesn't cause any motion to anything. And so the argument would be is that all of the all of the red force, okay, going this way and this way, is completely inert. All right, now I should do it on this one. So so this is the one we're going to use, is proton, electron, proton, because that's what's in the nucleus. 2 protons, 1 electron. So this is the core object. So instead of talking about neutrons and electrons and protons, this mechanism, this little object, is like the building block of atoms. This is what the nucleus is made out of. Because you can understand, every time you add a block, you're basically doing the same thing. You're going to end up with twice as many protons as electrons, and you're going to have the same positive net balance that nucleuses have. And so it works as a building block. And so, yeah, so the point would be is that all the green force that goes in here, okay, and all the green force that goes in here has absolutely no effect on the protons. But if I take some energy and I quickly knock that electron out of there, right? So this electron now has disappeared. All of a sudden, 1/2 of the total force in the universe, right, essentially is now going to be turned into red force, in terms of it's going to go, let's draw it a little bigger. All right. So we have 2 protons in space. So before, the green force was totally meaningless, couldn't do anything, all right? But now what's going to happen is it's going to be converted to red force in between 2 protons, right? So I kick the electron out, then I kick out the converter, and so now these 2 protons see 1/2 the total force in the universe is now capable of just creating very high pressure between them. So there's now all of this green force is going to be turned into force pushing against that proton. All of this green force is going to be converted into force pushing against that proton. So the 2 protons shoot out, at high speeds, very high. All right, and that's what is causing the chain reaction in a nuclear bomb, is just the fact that what you're really doing is breaking bonds controlled by an electron, by hitting an electron out and allowing the pressure to move between the 2. And you could understand that I could also do that, all right, if the atom is more complex, and I would end up with a circumstance where there was more than one, okay, of these objects, in the sense that there was another electron over here, okay, another electron over here. Now you could understand, if I popped this one out, I have the same circumstance, and you could say, okay, this is a neutron flying out at high speed, and this would be a neutron flying out at high speed. So this is where the pressure would be created, this intense pressure between the 2 protons, and it would just basically push this object that way and push that one that way. So they basically say, look, a chain reaction is basically 1 neutron goes in, this would be a neutron, and this would be a neutron, and 3 neutrons come out. And so that's what sustains a nuclear bomb, is the fact that for every incident of trouble you're creating 3 new troublemakers. And so that makes perfectly good sense. And so the same argument could be made about what is happening when we're fusing hydrogen. Now, you're not only not making hydrogen, what you're making are those deuterons. So this inside the sun, what's really happening is you have a bunch of hydrogens, okay, where there's distance between the nucleuses, the protons and the electrons. All right, and you're pushing those things together. All right, so I might draw one more. All right, and when in the process of allowing them to get into where more and more force is going to be pushing on them and causing the attractive force between them, enhancing the attractive force, the attraction, making it stronger and stronger as they're in denser and denser pressure. And you're basically just converting them into the neutrons. So what the sun's really doing is just converting hydrogen into neutrons. And then those neutrons, end up becoming deuterons. And then those deuterons end up becoming helium nuclei. And so for every one that you're making, though, the trick would be you can make one, and then because it is high pressure, every now and then a bit of high pressure is going to hit that electron, knock it out, and you're going to end up losing what you built. So the sun is destroying, it's making neutrons. And then in the process of making neutrons, some of the neutrons get broken. And then they create the bits flying off, that cause other catastrophes to take place. And it just has to do with how much of this fissionable material, you have, whether the sun eventually supernovas. So the denser and denser the sun gets, the more big nucleuses it has inside of it, the more likely it can sustain a chain reaction. And the less heavy elements it has, the less nucleuses that have grown bigger and bigger and bigger, the less likely it is to sustain a chain reaction. So, it works as an explanation. It's dirt simple. It doesn't have any of the complexities of their theory. Certainly doesn't have anything non-mechanical. Everything flies straight line trajectories. There's no shenanigans of any kind. Everything's just controlled by a mass and a velocity. There is no catches. And it works. But would they consider it? No. Did they consider it? No. Did they think about it much? No. They just accept the dogma. God says so, the 10 Commandments, whatever. And then they move along. And they never even think about it. It's just like the religious people. You say, it's kind of silly for them to worry about 10 Commandments when they came up with the do unto others as you'd have others do unto you. What do I need these 10 for if I have that one? It's just a logical statement saying, well, which one of these 10 isn't covered by this? Kiss God's feet? Yes, okay. The commandment that says kiss God's feet, all right, yeah, I don't really have to worry about that one. But all the others, not killing, not stealing, not coveting, not doing all that, covered by the if you don't want them to do it to you, don't do it to them. That statement covers all that. Did the religious people even think about it? No. It's just ridiculous. And that's what's this. The science is in the same atmosphere of just to believe what the popes and the bishops tell you. You're just dumb peasants. You're here to be duped and fooled. Just let them dupe and fool you, because that's how the system works. The people with the little funny hats and the little badges, they'll tell you what to think, and you don't do any of it on your own. You just believe what they tell you. So if they tell you there's flying rhinoceroses, you believe it. If they tell you there's dark matter, you believe it. If they tell you space is expanding, you believe it. Just believe whatever they tell you. And don't think about it. Don't scrutinize it. Don't say, well, isn't there some sort of alternative to believing that? But the very fact that they never even considered other models of the basic arrangement of the geometry, even though their chemistry has very fixed geometry. Then, if they make a chemical model, a ball model of an atom, they don't sit there and spin it and do all kinds of crap to it. No, they say, look, the electrons here, the proton, they have it all connected, and it looks just fine, and it works just fine. So why are you using this spinning? Why are you accepting this idea of all this stuff having orbits and all these trajectories and all this complexity when a simple magnetic model works? Alright, I think I'll take a pause there, and we'll see if I want to do more subjects. I mean, I take notes, and it gets so obvious that just these little simple statements, the idea that there's one universe, right? There's no point in talking about the big universe and all that kind of crap like that. That's a good place to get information, because all of that's made out of what electrons and protons are doing. The only universe is electron, proton, space, and the force. And that's it. There's no other universe but that little tiny one. And understanding that one will tell you what all the other bigger universes, why they do what they do. It'll be explained by the understanding the mechanisms that happen in that little one. And what have they done to that? They've pretended that that somehow nothing is in any position, okay, that somehow there's some sort of special way that you can look at something and it does some sort of collapsey thing, but when the universe looks, or if aliens look, or if something else's platypuses are looking at it, somehow it doesn't collapse. So even though it's constantly being bombarded by force, and every now and then we take a look and say, oh, is there any light outside? I mean, the light outside is only light outside when I look at it. Otherwise, it's not light. There's no photons unless I decide to make photons. I mean, it's just so bad. And you people just eat this crap. And you're just like, why are you looking up this science vomit? It's cheap, silly, babbly. It's so immature and unprocessed and incomplete, as Einstein would say. Why are you selling this as the truth? Why are you believing this? Why are you pumping this? Why are you pushing this? Why can't you just understand that, yes, this is not science. This is religion. They're just talking, mush and phantasmagorical wish. And it really doesn't have anything to do with where the evidence is really, the hard evidence is pointing. I mean, the very fact that we can't bang a laser beam into a laser beam should tell everybody that, well, if they're going to tell me that photons, interfere with each other, well, they have to explain how they can do that exactly. And then they say the photon is now interfering with itself. And I've already been through all those arguments, but the math doesn't match their drawings. It's all just such a fraud and a lie. This thing can mechanically be understood. It's just point sources and locations. You're drawing vectors, and they're either in phase or out of phase based on the length of those vectors. It's really not complicated. Now I'll pause. But you can go on, and there's so much of it. It's so bad, and I just don't know why you're all pushing that crap. Alright, I guess I'll throw in a little bit. So let's say I had a dipole, right? An electron and a proton. And you could, and you're saying, okay, what if I did do that obvious thing, which means there's another electron over here. Okay. So you could have a proton, electron, electron, or you can have electron, proton, proton. And you could sort of obviously think that, well, what about this other dimension? I could also do the same thing. And you could probably do it in a way where these two are canted this way and that way, and then these two would be canted this way and that way, and then that would maximize the distance between the repulsive pieces. So it'd be pretty easy to start the geometry, but the geometry would basically be made out of that idea of, for every electron, there's 2 protons. And then you could understand that, okay, if I made something out of that, there would be places I would look at it, I'd see green. And then if I turned it and looked at it from this side, I'd see the red. So depending on which way I turned it, I would see a pole. And that sort of fits for atoms, right? So if atoms are sitting in a substance, you could argue that they're not just, I guess I could draw that. They're not just dipoles, like this side of the atom is positive and this side is negative. it's more likely, okay, I mean south and north, okay, it's more likely that it's south and north over here, that the polarities match the arrangement of the objects, and that the geometry of the polarization is not at 180 degrees but at 90 degrees. That you have lots of 90-degree polarization, where you go from South Pole to North Pole to South Pole to North Pole. So anyway, so it's just another part of physics that wasn't considered. Now that really starts to explain why, when you put electricity through and compress atoms and stretch them, that you end up with a magnetic field, okay, that can be perpendicular but also directional, okay. And so that's another whole, you could argue that the only distinction between electricity, the electric field, and the magnetic field is the magnetic pattern is at an angle, a 45-degree angle, and the electric field is the straight line field because it's simpler. But anyway, I won't get into all that. But I mean, I'm just saying it answers so many questions about why is the magnetic field directional, all kinds of stuff, the right-hand rule, But anyway, and theirs is just that they're just made up axioms. They just tell you. And yes, some of the things they say are true. Okay, there is a right-hand rule for a good reason, but they have no physical explanation for why it exists. Nothing in their mechanics explains it. Just like they have no mechanical explanation for gravity or drag, which is a real thing. Electrons and protons are dragged. Why aren't deuterons dragged? Well, I've sort of explained why they're not dragged. Is because any velocity this back seat driver has can never be opposed as long as this object exists in front of it, because it'll convert all of the energy that would oppose this motion into energy that's inert to this object. So its capacity to push never changes unless you rearrange the filter, the thing protecting it from the force, the shield. Alright. So the next video I think it's going to be Stern Gerlach again. I saw some video by one of these shitheads, and they know so little. They just jump to these extraordinary conclusions based on tiny little pieces of insight, and it's not good science. Science isn't jumping to conclusions. Science is rigorously testing. Alright, anyway, till the next time, keep doing the experiment all kinds of ways. Try it all kinds of ways to see if you can really figure out what the variables that are controlling the experiment are. And they don't do any of that. They just try to prove their fantasies. Alright, anyway, till the next time and such.